Good morning. My name is José Roberto de Almeida Amazonas, and I will present the paper Low Complexity Nano-Networks, Routing Scenarios and Strategies. This paper was developed by myself and my colleagues, Professors Xavier Ressalba and William Ferreira Josa. The paper has been published last year. In this work, we focus on electromagnetics nanocommunications as it is currently the most promising in terms of practical implementation in the near future. We focus on the network layer that can be seen in this figure that shows our architecture model. And the contributions may be summarized as the formulation of the nano-networks routing problem, a proposal of a low-complexity finite-state machine-based paradigm to implement routes generation and routing algorithms, and evaluation of the proposed nano-networks routing strategy. The table that you are seeing now on the screen summarizes the main related works. We provide a classification in terms of path selection that can be single path and multipath, the forwarding strategy that can be unicast, multicast, or broadcast, the topology that is considered where we can have flooding, where the knowledge of the topology is not necessary, or the awareness of the topology that may be physical or logical. We consider the papers considers the dimensions of 2 dimensions or 3 dimensions, and some of them consider node mobility. It's important to see here that all works that we summarize here have our knowledge of the nano-networks topology, and this is not a very realistic hypothesis. So in this work, we propose a novel forwarding and routing low complexity and flexible strategy for nano-networks based on finite state machines. Finite state machines allow to build a logical nanonode addressing scheme of low complexity that provides the flexibility to implement different strategies of multipath, multicast routing, and forwarding, single hop, multi-hop, flooding, physical or logical clustering, mobility, 2D or 3D nanonode deployment. Resilience is implemented by means of the multipath routing and forwarding strategy. And the generation procedure avoids the building and storage of routing tables, does not need any signaling routine to discover neighboring nodes, which saves energy and minimizes latency. In order to perform network complex computations, processing workloads are moved to upper layers of the adopted architecture, where high-performance devices are provided. Here you have again a figure depicting the architecture model. Going from the top to the bottom layer, the first one is the network function virtualization layer, where network complex computations processing are performed. In case of major computational requirements, the NFV layer is able to provide resources from small or even big high-performance centers. The next 2 layers, IoT layer and SDN layer. The SDN layer, meaning software-defined network layer, provides flexible control of the traffic to be transmitted. It's also used to facilitate the provisioning of IoT functionalities in the upper layer, such as addressing and simple network services. Next, we have the nano-network layer that contains the nano devices, providing the basic physical functions required to be able to exchange information, signals, mechanical issues, frequencies, modulation schemes, medium access control strategies. According to this model, the nano-network layer encompasses the functions of the physical, MAC, and network layers. The functions that we adopted in this work is shown in this table. It's not necessary to implement all of them. The choice of the functions depends on the applications that we have. Just to provide some examples, the first function, activate, is generated by the controller to trigger the nano device by sending a signal to a certain nano device's ID to make it active on a specific time. Nano device's ID can be a specific device or a group of devices. As another example, we have the function move. This function is also generated by the controller and sent to the nano device. It drives a nano device with a certain ID to a deterministic location. And for example, the function listen. This function is generated by the nano device and it is received by the controller to listen the possible coming messages from a nano device with a specific ID. Finite state machine-based routes generation. It's very important to take into account that the resources available in nanoroutes are very limited. This being so, the main requirements are avoidance of routing tables to save the resources that are necessary to build and store the tables, avoidance of any signaling routine to discover neighboring nodes to save energy and minimize latency. Few years ago, it has been proposed the trellis-coded networks, TCNets for short, that have the following main advantages: elimination of routing tables, reduced latency because no signaling messages exchange is necessary, as is the case of the more traditional protocols. Self-recovery mechanism in case of failure derived from the robustness of the trellis decoding mechanisms. The figure on the right side of the slide shows the main concept of TCNet. On the upper part, we have a finite state machine. In this machine, we represent two states, state I and state J. Receiving an input sequence K of n, the machine produces an output out of n and has a transition from state I to state J. Each state represents a node in the network, and a transition from state A to state J represents the transmission of a data packet from node I to node J. Figure 3 shows an 8 states finite state machines. Here in the middle of the figure, we have a shift register. In the shift register, for this case, the S2, S1, and S0 represent the current state of the machine, and S3, S2, and S1 represent the next state of the machine. The input of the machine is the sequence K of n. In this specific case, two outputs are generated using exclusive OR operations of chosen states. In this work, we do not use the output sequence out of n. That is an essential feature to deal with transmission errors, node failures, hidden and exposed nodes. These aspects will be dealt with in future work. As an example, let's consider a nano-network with 32 nodes. So it is logically represented by a finite state machines with 32 states. The states are represented then by 5 bits, and the next state is obtained shifting in 2 bits, the sequence K of n, K1, and K0. So if the current state is represented by S4, S3, S2, S1, and S0, the next state is then represented by K1, K0, S4, S3, and S2. Let's consider that we want to make a transmission from source node S equal to 12, and the destination node D is equal to 23. So the IDs are, for node 12 is 0, 1, 1, 0, 0, and for node 23, it is 1, 0, 1, 1, 1. The first case is of direct paths. So the initial state corresponds to the node 12 ID, 0, 1, 1, 0, 0. And the final state in this case is K1, K0, 0, 1, 1. And it's always different from the destination node that has 3 ones as the less significant bits. So there is no direct path between source and destination. Case 2, we consider a 2 hops path. So in this case, we have an input sequence that is K3, K2, K1, K0, that is input to the machine, and the final state is K3, K2, K1, K0, and 0. That is always different from the destination node. So there is no 2 hops path between source and destination. The third case, we consider 3 hops paths. So the input sequence has 6 bits. The final state is K5, K4, K3, K2, K1. That is made equal to the destination ID, and this sets the values of K5 through K1. But for K0, we have 2 possible choices, meaning that we have 2 distinct paths between source and destination. In the first one, K0 is equal to 0, and the traversed states are 12, 19, 28, and 23. And the second case, K0 is equal to 1, and the traversed states are 12, 27, 30, and 23. As general conclusions, we have that increasing the length of the input sequence, longer paths may be generated. The procedure to generate paths of any length is very simple, and it is sufficient to assign the logical ID of the destination node to the most significant bits of the input sequence K of n and generate all possible combinations for the remaining bits of K of n. And the procedure may be followed by a filtering algorithms to select, for example, only disjoint roads or to avoid any specific node. The novel scenarios strategies. We consider then that the nodes have very few resources available in terms of energy storage processing power. The nodes have a high failure rate, being not available to perform any tasks. The nodes may be distributed in such a way that the network is not connected. The nodes may not know their physical location, and the nodes may be highly mobile. It can be said that in general terms, routing has to be provided for a network with unknown and changing topology. This figure is an example of the use of three different power transmission or transmission ranges. In the first case, the transmission range is equal to 1, so only the blue node, that is the transmission node, is within this circle. Increasing the transmission range to 2, the three nodes in red can be reached, and increasing again the transmission range to 3, the nodes in yellow can be reached. The metrics that are used to evaluate the strategy are the packet delivery ratio, the average number of nodes that is evaluated considering only the roads that are able to deliver a packet to the destination, and it is a measure of the average latency, and the energy consumption per packet, that is the sum of the energy spent by each node participating in the route. So you have the model that is considered here. We needed to consider the energy necessary to generate a route, to transmit a packet, to forward a packet, to receive a packet, and to decode a packet. In terms of the energy that is necessary to transmit a packet, it is given by equation 1, where we have the transmission rate to the power of alpha tx, that is a model of the propagation environment. And then for a route from source S to destination D, the energy that is necessary is given by equation 2, where we have the energy consumed by the source. The second term is the energy consumed by the intermediate nodes, also called hidden nodes, and then the energy consumed by the destination, and each of these terms are given respectively by equations 3, 4, and 5. In terms of evaluation and results, the parameters that have been used in the simulations are summarized here. We consider the topology is random and uniform over a 10 by 10 area, denoted by A. The transmission range varies in unit steps from N up to covering completely the area of the network. The density of nodes that are considered are from 0.16 up to 1.28. And the scenario has the following characteristics. Each node, meaning nano-router, has an individual logical identity. The nodes do not know their physical position. The nodes do not store any routing table. The source nodes generate a certain number of routes to the destination node. The source node transmits a packet corresponding to each generated route. All nodes in the route transmit in broadcast mode and use the same transmission power. All nodes have means to detect duplicate packets and to discard them. The routing generation process is described by two parameters, the case sequence and the maximum number of hops. So the simulation parameters are summarized in table 5. And for this topology and the simulation parameters given above, a total of 275 routes have been generated. And for each of these routes, the minimum transmission range to make the route valid was evaluated, and the distribution is given in figure 10. So you may see that we have a peak of 76 routes needing a transmission range of 8 to guarantee that the destination is reached. Here you have a comparison between the finite state machine procedure and the flooding procedure. The first figure, we have the packet delivery rate, and you see that flooding achieve 100% packet delivery rate with a transmission range of 2. While for the finite state machine, it's necessary a transmission range of 8 or 9 to have the same packet delivery rate. However, we see that using 275 paths to send the message from reference source node to all the destinations represent a waste of energy. And the second figure, we have the total energy consumed by each of the techniques. You see that flooding consumes less energy than the finite state machines, but this result is the result obtained considering all the 275 paths. But we can optimize this result in two different ways. The first way, the case 1, that is the red line, the criterion is to choose the smallest transmission range, and then we choose just the best route. In this case, the finite state-based scheme requires a total energy of 4,837 against the flooding-based scheme that requires an energy of 94,507. Another criterion may be used, that is the smallest latency, meaning the minimum number of hops, and we see again that the finite state machine-based scheme is superior to the flooding-based scheme. As conclusions, for all simulated cases, the finite state machine-based strategy has shown a total energy consumption much lower than a simple flooding-based schemes. So this approach seems to be very promising, and in future work will investigate how to enhance and to improve the performance when the nanorouters are spread over a large area, how to exploit resilience of the trellis decoding to demonstrate the robustness of the approach in the presence of failures, how to mitigate problems related to hidden and exposed nodes, and how to deal with mobility. The new scenarios will be studied. Two of them will further exploit the possibility of implementing routing and forwarding strategies without awareness of the physical topology, introduction of logical clustering, and the introduction of relay functionality without increasing the complexity of nanorouters. Thank you.